Hi everyone, Mrs. Hanson here, looking at a next lesson in our chemical equilibrium chapter on Le Chatelier's principle. Now isn't that just a fun name to say, Le Chatelier's principle? We have been studying systems that are in dynamic equilibrium, and we have suggested that the equilibrium constant is just that. It is a constant called K. Kc and Kp have the two equilibrium constants we've been focusing on thus far in our chapter. That word constant means that that number is consistent no matter what the initial reactant concentrations or product concentrations, the system will react to create a dynamic equilibrium state of a constant value. Now, Le Chatelier's principle studied this, and it reads, if a stress is applied to a system, and that system is at equilibrium, the position of the equilibrium will shift to reduce the stress. Whatever you do to the system to apply a stress, that system will counteract it to alleviate or eliminate the stress. Well, what are stresses? There are three types of stresses, and we're going to look at them one at a time. One is to change the concentration of either the reactant or the products. By changing concentration of the reactants or of products, we create a stress, and the system is going to do the opposite to alleviate the stress. If I add more, it will want to use it up, and so forth. There is the second type of stress, and that is to change the pressure of a gaseous system, and we do that by changing volume. And we'll look at that specifically. And the third stress we'll talk about in this lesson is changing the temperature. We know that equilibrium constants are temperature dependent, so not only would it shift the equilibrium, it would change the equilibrium constant. Le Chatelier's principle, if a stress is applied to a system at equilibrium, the position of the equilibrium will shift to reduce the stress. And that stress will either be changing concentration, changing pressure by changing volume, or by changing the temperature. Let's explore each of these in detail. We said the first stress was changing the amount of reactants and or product. Now let's just take a look at an example equation, shall we? Let's suppose we have reactant A with reactant B in dynamic equilibrium, making product C, and just some general equations. At the system in dynamic equilibrium, we have a K, which is a constant, the equilibrium constant. If I add more product, such as letter C, that's my made-up letter there to represent the product, increasing the concentration of a product is a stress. Now, what's the opposite of more C? Well, that's less C. So that's saying that the system is going to counteract that by shifting left to use up the excess C and reestablish equilibrium. If I increase the product, the reaction will shift left. And the reason that is said is because the reaction quotient becomes larger than the equilibrium constant. So we want to reestablish using up the excess C means to point away from it. Pointing away consumes the excess product, making more A and B along the way. So if this is the initial stress, just to kind of think about, the initial stress is increasing the amount of product. When we shift to the left, shifting left is going to use excess amounts of C up, and it's going to make more A and B because we're pointing at it. So adding product shifts the equilibrium left to reestablish a quantity so that the ratio of product over reactants resumes to the K constant. What if we add or remove, kind of in a second example, what if we remove a reactant? Well, let's take a look at that. If the stress is removing reactant A, if the initial stress is to take away letter A, what's the opposite of that? Well, if you remove A, the system will want to make more. And to make more, you better point at it. So by removing reactant A, the equilibrium will shift left. It does so to produce more quantity A and reestablish the equilibrium constant. As the reaction shifts left, product C gets used. Reactant B would get made along the way, and that's to reestablish the quantity of reactant A. How about the opposite of taking away reactant A? What if we make a stress where we increase the amount of A? Adding a reactant. Well, again, if you add letter A, the system wants to counteract that stress by using it up. And to use up, you got to point away from it. If I increase the amount of reactant A, the reaction is going to shift to the right. I don't know why I wrote left. It's going to shift to the right to use up the excess A. And as it does so, letter B gets consumed and letter C would get made. And you'll reestablish the ratio of products over reactants to become a constant, reestablishing the equilibrium constant K. If you remove a product, let's just say we remove letter C, you're going to want to point at letter C to make more, and therefore the reaction would shift to the right. So once you determine the effect on the reaction quotient, it will tell you the direction of the shift. Do we need to make more product? Do we need to make more reactant to reestablish the equilibrium constant K? Adding product shifts it to the left. Removing reactant shifts it to the left. Adding reactant shifts the equation to the right. And determining the effect on the reaction quotient will tell us the direction of the shift. Let's give it some thought. Here we have a reaction. 2 units of NO in the gaseous phase reacts with a molecule of oxygen in the gaseous phase, and it's in dynamic equilibrium with 2 molecules of NO2, also in the gaseous phase. Let's suppose we upset this equilibrium by adding oxygen. So here's my stress. The stress for this equilibrium is increasing a reactant. I'm going to add more oxygen. What will the system do to alleviate or eliminate or reduce the stress? Get rid of it. Well, the system is going to do the opposite of what you did. If I added more oxygen, it wants to use it up to alleviate that stress. And if there's, excess stress is the oxygen, you better point away from it. Pointing away consumes the excess oxygen. And we say that this equilibrium shifts to the right. As it shifts to the right, the NO gets consumed, that excess oxygen gets consumed, and more product would be made. So you've reestablished the equilibrium constant by shifting the equilibrium to the right. In a next example, it says, suppose NO is removed. So in the second example, let's suppose the initial stress is the removal of NO. Well, decreasing concentration of NO is the stress, and therefore the opposite of that is making more. To make more of it, you better point at it. If you decrease the concentration of NO, the equilibrium will shift to the left. Along the way, as it shifts to the left, NO2 gets consumed, more oxygen would get made, and more NO would get made, therefore reducing the system's stress. Equilibrium has been reestablished by changing concentrations of each of these ingredients so that the ratio of product over reactants yields back the equilibrium constant K. A second stress is changing pressure, and changing pressure specifically of gaseous reactants and products. Now remember, it's only in the gaseous phase that those systems would even create a pressure. Think of pressure as just collisions against the side of the container of a reaction vessel. So just to kind of go back to gas laws and thinking about Boyle's law, let's have a system. Let's just have a piston of contained gas molecules. And if you reduce the volume by pushing down on the piston, right, if you decrease volume, you can see here the pressure would increase because you'll have more collisions in that time. So decreasing volume, increasing pressure. So just kind of think about this. You learned this as Boyle's law. By reducing the volume, you can change the pressure of a system, and that creates a stress of a system that's in dynamic equilibrium. The system is going to move in the direction that has the least moles of gaseous particles. Think about low pressure has the fewest particles. High pressure has the most moles of particles. So therefore, when we change volume, therefore changing pressure, we have to decide which side of the dynamic equilibrium will have the lowest pressure or the highest pressure by looking at the number of gaseous moles on either side of the arrow. So let's model that thought, and we'll do that by, well, let's look at an example of, how about making ammonia? Let me go back to the screen here, and I'll just add a little example here. We know that a gaseous mole of nitrogen reacts with 3 gaseous moles of hydrogen to produce 2 gaseous moles of ammonia. All of these are in the gaseous phase. We've learned this to be the Haber process. Alrighty. So just to kind of clarify, there is 1 plus 3 is 4 gaseous moles of reactants compared to 2 gaseous moles of product. Now let's suppose in this system, let's say that the stress that we're going to apply, if we apply a stress, let's say we decrease volume. And that's what it would say in the problem. You've decreased the volume as your stress. What will this system do, according to Le Chatelier's principle, to alleviate or eliminate the stress and reestablish dynamic equilibrium? When you read that you've decreased volume, I want you to interpret that by really seeing that the stress is increasing pressure. Pressure and volume are inversely related. So by decreasing the volume of your reaction vessel, you've increased the pressure. How will the system react? So the system wants to counteract this. The system wants to do the opposite. The system will decrease pressure. To alleviate the stress, it wants to drop the pressure. In which side of the equilibrium will have the lower pressure is the side that has the fewest gaseous moles. This equilibrium will shift to the right to alleviate that increased pressure. And it does so by taking 4 gaseous moles and converting them to fewer particles. Fewer particles means fewer collisions, and the pressure of the system will drop, and equilibrium has been reestablished. Opposite is true as well with this equation. What if the initial stress said we have increased volume? That's my doorbell. If you increased volume, interpret that as saying the stress is actually decreased pressure. Pressure and volume are inversely related. So if the stress is dropping pressure, what will the system want to do to counteract that stress? The system will want to increase the pressure to reestablish the equilibrium. And to increase pressure, you want to have the side with the greatest number of gaseous moles. And that, of course, we said was the reactant side. So this equilibrium will shift left to increase pressure, having more gaseous particles, therefore more collisions, and it will have reestablished the equilibrium. When we change pressure, we typically do so by changing volume of the reaction vessel. What we might also see is adding an inert gas to the system. So think about what an inert gas might be. Another name for inert gas might be the noble gases, such as helium, argon, neon, krypton, radon, all of those in group 8A. Those are all examples of inert gases. The inert gas is a gas that's not part of the reactants or products. It's something else related to reactants or products. So for instance, just to go through the Haber process again, and I show you this balanced equation, all gaseous phases of matter, 4 gaseous moles on the left, 2 gaseous moles on the right, and I add an inert gas. So let's say the stress is I add, let's say, argon. Notice that there is no argon anywhere in this equation. It's not a reactant, it's not a product. Therefore, it will have no effect on the established equilibrium. It'll change the pressure of the reaction vessel, but it doesn't shift the equilibrium because it's not a reactant or product. So no effect by adding an inert gas, a gas that doesn't partake in the actual chemistry of the system. Let's try this one. Here I have an equation where I have 2 gaseous moles of sulfur dioxide reacting with 1 gaseous mole of oxygen, setting up a dynamic equilibrium of 2 molecules of sulfur trioxide. Notice I have 2 plus 1 is 3 gaseous moles of reactants. On the product side, we have 2 gaseous moles. More particles, higher pressure. Fewer particles, lower pressure, because pressure is defined as the number of collisions within that reaction vessel. Here's the stress. If the volume of the system is increased, what happens to the system? So if I increase the volume, I want you to read that as in your head saying, oh, what I've really done is dropped the pressure. That's the stress. By dropping pressure, the system wants to counteract that, and the system will do is shift to the side that will raise the pressure. And the side that has greatest pressure has more gaseous moles. Therefore, what we will see is that this equilibrium will shift to the left to raise the pressure. If I increase the volume, the pressure drops. The system is going to want to raise the pressure, and it will do so by shifting to the left to create more gaseous moles. And then this asks also if argon is added to the reaction vessel, causing an increase in pressure. Argon. Argon is one of those inert gases we just talked about. I don't see argon in this balanced equation anywhere. Since this is an inert gas, it will have no effect on equilibrium. Changing the temperature. Well, remember that equilibrium is temperature dependent. Therefore, it affects the rates of both the forward and the reverse reaction. They both increase in terms of their kinetics. And I know kinetics is an upcoming chapter for us yet, but just think of kinetics. The rate of disappearance of reactants or the rate of appearance of products. So it doesn't just change the equilibrium position, but it's the K constant that will actually change as well. And the direction of this shift is going to depend upon if the reaction is exothermic, heat releasing, or if it's endothermic, heat absorbing. And let's take a look at how this works with some examples. Remember that the enthalpy change, and I'll just write that up here, is the enthalpy change, delta H, is less than 0. We said it's a negative value. It's heat releasing, exothermic reaction. I want you to think about that in terms of heat being a product. Just like products come out of the reaction, heat comes out of the reaction. Let's suppose I go back and I show a thermochemical equation, and I'll just show, how about methane plus oxygen in dynamic equilibrium with carbon dioxide and water. And I'm just going to show the delta H of this reaction is negative 45 kJs per mole. There. So what I'm saying is, when I see this as an exothermic reaction, I know that because the delta H sign is negative, you can rewrite this equation just by saying methane plus oxygen is in dynamic equilibrium with the carbon dioxide, water, and just think about this as heat energy coming out of the reaction. Just write it as plus heat. And therefore, you can see very quickly what happens to temperature changes just by considering it as a product. If the stress says, let's increase the heat, what's the opposite of more heat? Well, you're going to want to use that up so you know that you're going to have to point away from it to consume the excess heat. Therefore, it will shift left. What about the opposite? Let's say the stress is decreasing heat. If you decrease the heat as the stress of the system will want to make more heat, therefore you're going to point at it. And you will say the reaction will shift to the right if I decrease the heat of an exothermic reaction. Treat heat as a product coming out of the equation. What about endothermic? If we have an endothermic and the delta H comes out to be a positive number, I want you to think of that as absorbing heat. That's a wrong word, right? Just like a reactant, you have to place heat in to get the reaction going. So let's say, for example, elemental hydrogen plus iodine combine to make 2HI. And the delta H for this reaction is given as positive 100 kilojoules per mole. I see the positive sign and I know that it's endothermic. So in your head, just think of this equation, instead of having the delta H at the end, put it right here as a reactant and just call it heat. Heat is required for this reaction to occur. So treat it as a reactant. If the stress says, let's increase the heat of an endothermic reaction, what will happen to reestablish the equilibrium? Well, if the stress is more heat, you want to get rid of the excess heat and you're going to shift to the right, point away from it to consume the excess heat. Adding heat to an endothermic reaction drives the reaction to the right. And let's suppose the stress was decreasing the heat of an endothermic reaction. If you decrease the heat, you want to make more. So you better point at it. Therefore, you would know that the reaction would shift to the left if you decrease heat of an endothermic reaction. And remember, K constants change when temperature change. K constants remain the same for changing concentrations of pressure, changing concentrations or changing pressure, but the K constant will have a new value if you change the temperature. Let's look at this one. It says try this, and we're going to kind of walk through it together. Here's my equation in which I have dinitrogen tetraoxide, N2O4, in the gaseous phase, in dynamic equilibrium with 2 molecules of nitrogen dioxide, also in the gaseous phase. The enthalpy of reaction is given as positive 58 kJs. So when you look at this equation and you see that this is a positive endothermic value, it is a wise idea to just think of the equation as including heat on the left side, just as you would a reactant, and reading that simply by saying heat is required for N2O4 to decompose into 2 molecules of NO2. Now we're able to kind of go through and practice the equilibrium shift. Let's suppose I have a stress applied to the system, and that stress, I'll call this letter A, B, C. The stress in letter A is to increase N2O4. So here's my stress, increasing N2O4. Well, what will the system do? It wants to decrease the quantity to reestablish equilibrium, and to decrease that amount, you've got to point away from it so it's consumed. N2O4, adding N2O4 is going to cause the equilibrium to shift to the right. How about letter B? In letter B it says NO2 is removed. So now here's the stress, removing NO2. To alleviate this stress, you want to make more. And to make more of the NO2, you better point at it, right? You point at the products that are being made. And so therefore, we would know that NO2 removal would cause the equilibrium to shift to the right. How about letter C? Total pressure is increased by the addition of nitrogen molecules. Well, N2, I don't see N2 by itself in its elemental form in either reactant or product. So this is not part of the system that we're studying. Increasing the total pressure by adding a gas that's not involved in the equilibrium that we're studying has no effect. It will not cause the equilibrium to shift left or to shift right. How about letter D? I'll call this D. The volume is increased. When you say volume is increased, what I need you to hear in your head is that you've dropped the pressure. And so the stress is dropping pressure. We want to counteract that stress by raising pressure. And to raise pressure, we need the side with the most gaseous molecules. So which side has more gaseous molecules? Well, on the left side, there's just 1 gaseous mole, and on the right side, there's 2 gaseous moles. So by dropping pressure, the system wants to raise the pressure, and it will do so by favoring the side with the most gaseous moles, so it will push to the right. Letter E, temperature is decreased. Now this is very specific to the temperature, So if the temperature drops, think of that as removal of heat on the left side of your arrow. Therefore, you're going to want to make more heat, and therefore the equilibrium will shift to the left. Let's do a little review problem here. It says using the standard heat of formation, which is found in the appendix values, and really they're just given to us either in the homework problem or in a quiz. They'll be put right into the actual problem itself. We want to determine the standard enthalpy change for this reaction. Well, all right, let's take this one step at a time. We have a reaction where we see nitrogen reacting with hydrogen, forming 2 gaseous moles of ammonia. So let's repair this, get it written correctly. We have a 1:3:2 stoichiometric ratio. And I know that delta H of formation, those are in your thermodynamic table, that for any element in its natural state, we know that it's assigned a 0. So nitrogen in its natural state, the heat of formation is assigned a 0. Here's hydrogen in its elemental form. The heat of formation then therefore is defined as 0. And I just went ahead and pulled this before I started the recording. I found negative 43.19. The elemental form of nitrogen, hydrogen combining to make ammonia, giving me an NH3 value from Appendix C is 43.19, exothermic, so you'll see a negative sign. And this one is quite simple because it's going to say the delta H of the reaction can be found by taking the sum, well, that's a funny sigma, the sum of the products minus the sum of the reactants, remember from our thermo unit. But this equation turns out to be quite simple because these are both 0. So the products, my coefficient of 2 times the enthalpy value per mole is 43.19 minus the sum of the heat of formation for those elements, which is just 0, right? So see how easy this becomes? Once I looked in the table or the appendix for the enthalpy value, heat of formation of ammonia, found it to be 43.19 times 2. This comes out to be an exothermic value of 86.38 kilojoules. So what that's really saying is I can add that right here. The delta H is negative for exothermic, 86.38 kilojoules of heat for this equation, as written. And most importantly, we can see that it's an exothermic value. So determine how the equilibrium constant for this reaction should change with temperature. So here's what we're thinking, right? When you look at an exothermic reaction, I want you to just consider that as coming out of the reaction as heat. So just write it plus heat as the product. And it says, how does this change with the temperature changing? So it's exothermic. Let's suppose I increase heat of an exothermic reaction. The system will shift to the left to use up the excess heat. And what happens to the number of the equilibrium constant? Well, as I shift left, I use up the ammonia and I make more reactants. Remember that K is the relationship of the amount of ammonia product squared based on its coefficient times the molar concentrations or partial pressures if we're looking at gases and atmospheres. This is the expression for this. And we know that if the top number decreases and the bottom number increases, you're dividing by a larger number, K is going to get smaller as the reaction shifts left. The equilibrium constant decreases as the reaction shifts left. The same is also true for the opposite, right? If we lowered the heat of an exothermic reaction, if the stress now becomes where you lower the heat, you're going to shift to the right to make more heat. Therefore, you're going to increase the products, decrease the reactants. The equilibrium constant, therefore, gets larger, favoring the product side. So equilibrium constant decreases because it's favoring the reactants. And the equilibrium constant gets larger when you favor the products. And this one, using our thermodynamic data in Appendix C, let's determine the enthalpy of reaction for this equation. I have 2 units of POCl3. And again, I looked up for us already that this is negative 542.2 kilojoules. And it's in dynamic equilibrium with phosphorus trichloride and molecular oxygen. Phosphorus trichloride, I looked up earlier, and it's negative 288.07. And of course, any element in its natural state has a heat of formation assigned as 0. We want to know overall, is this reaction going to be endothermic or exothermic, to make predictions on the equilibrium constant. And just as a reminder to integrate our last couple thermodynamic lessons, heat of reaction is going to be equal to the sum of the products minus reactants. I have 2 moles of PCl3, each at a value of 288.07 kilojoules. Plus 0, obviously, for the oxygen because it's in its elemental form. And I have 2 gaseous moles of POCl3 on the reactant side, each at a value of negative 542.2. So the enthalpy of this reaction is found by taking the sum of the products minus reactants. 2 times negative 288.07 minus 2 times negative 542.2. And this comes out to be a positive value. And therefore, I know that this becomes an endothermic reaction. And now I can think of heat over here as being on the reactant side. I have to input heat to force the reaction to occur. So if my stress is increasing heat, if you increase the heat of an endothermic reaction, the system is going to shift to the right to use up the excess heat, and therefore the products are favored, and therefore we know the equilibrium constant will get larger. And the opposite is true as well. If the stress was to decrease heat, the reaction would shift to the left. Shifting to the left favors the reactants, and the equilibrium constant will get smaller. We've talked about 3 stresses: changing in concentration, changing in the pressure volume, and changing the temperature, all in relationship to Le Chatelier's principle. I now would like to demonstrate 3 applications of Le Chatelier, and you'll see these in the next clip. I did some reactions underneath my document camera for you to see and get a visual of Le Chatelier. I want to make one last note, I guess, while I still have you before you leave, for those catalysts. Increase the rate at which the equilibrium is achieved, but again, no effect on the shifting of the equilibrium left or right. So adding a catalyst, no effect on equilibrium. Take a quick peek at these demonstrations I've made and apply Le Chatelier.